So now, be sure students can recognize various graphs, activation energy, pH, and temperature. But then look, they stuck another one in here. They snuck this in. They also want you to be able to identify factors such as pH and temperature that they had down here, but also concentration. They snuck that one in here, and that might also show up in graph form. So here we go with that, okay? And I'm going to start with the concentration thing. That is a variable. In a cell at any one point in time, you can have a whole lot of substrate, or you can have not so much substrate. You can also have a whole lot of enzyme and less enzyme, but we're going to stick with substrate concentration and what difference it makes in reaction speed. So if I put number of reactions over here on the y-axis, why do I want to put it there? Because it's the dependent variable. What's the speed or number of reactions depend on? In this case, we're saying substrate concentration. This should make sense to you, right? If we almost like kind of feed an enzyme more substrate molecules, if the substrate molecule concentration increases, what do you think the reaction rate's going to do? Well, it's going to be able to make more reactions happen with more substrate, more reactants. But not forever and ever. Because remember, we said these enzymes have a speed limit called its turnover number. And while it's very, very high, it's still a limit. And when the enzymes in our cell reach their speed limit, no matter how much more substrate we give them, then they can only work at that speed. They won't go slower, but they'll flatline. Their rate will stay the same. So this is what a graph would look like if substrate concentration was the independent variable, the speed of reaction depending on it. It would increase as you increase substrate concentration. That's your description of it. What's your explanation? Remember, that means what's the reason? Well, if you think about it, this should be pretty simple too. What's chemical reactions all about? Collisions. If we have more substrate molecules, we're having more collisions. What's the key collision though? Substrate enzyme collisions are increasing here as you increase the amount of substrate. And those are the key collisions because the enzyme helps reactions happen so much faster. So now let's look at pH and temperature, and I think temperature's first, I think. Yes, it is. This is a very common graph. This shows two different enzymes. They're just kind of a general typical one, and then a little more specific, an enzyme that works really well when it's really hot. Notice these are degrees Celsius, right? So your body temperature is more in this kind of range. And so what does this graph say? Describe what this graph says. Well, let's just look at this one. Let's forget the red line one for a second. It says that as you turn the temperature up, the rate of reaction goes up. Well, that should make sense. That was kind of like the Cheeto, right? But why? Now explain this positive slope part mathematically, right? Why as this increases, does this increase? Again, it's collisions. What's temperature all about? Speed of movement. Faster movement, higher temperature. So if we increase the temperature, what that means is we are adding energy to this system to make the particles move faster. What's that mean? More collisions. What are the key collisions? The ones, again, where enzyme and substrate are bumping into each other. Because when that happens, now the reaction happens a lot faster. But now look at this. If we keep increasing the temperature, unlike when we kept increasing the substrate concentration, this enzyme doesn't reach some kind of limit and then just continue. It doesn't work hardly at all in a very short period of time or actually temperature increase. Why is that? Well, now there's another factor involved. As the temperature increases, there's still more collisions happening. But there's so many collisions and they're happening so hard that the enzyme starts to break up, denature. And when it doesn't work, when the substrate bumps into an enzyme that the active site is now the wrong shape, then that incredible amount of help that enzymes gave to the reaction is not happening, and the speed of reactions falls off the table, so to speak. It doesn't go to zero because this substrate is still having reactions happen, especially because it's still bumping into itself a lot more, but the enzymes help so much that the effective rate goes off the table. Now, what this shows is that in our world, we have some places that are really hot compared to more normal temperatures around here in the 20s and 30s Celsius, right? And what we found are some organisms, like bacteria, some bacteria, can live in very hot places because at this hot temperature, this enzyme featured here is pulled and tugged and beaten, so to speak, into its right shape, its shape that it works. So, what happens if the temperature is really cold? Well, the enzyme is still working, it's the right shape, but when it's really cold, there are fewer collisions. So that's why as the temperature goes down, you have less reactions. It's not because you're hurting the enzyme shape, it's because the particles are just moving more slowly. Now we go to pH. Here you see a similar shape to the temperature graphs, right? You see goes up and goes down as the pH goes from here to there. Here you also see two different enzymes. These are specific ones they named for you. And again, they said they're not going to ask you to memorize specific enzymes, but they might tell you a story about pepsin and trypsin, like they very likely will, right? Notice one thing first. Pepsin and trypsin don't have ASE at the end. There's a simple reason for this. These are two enzymes that were among the earliest discovered. They are part of digesting your lunch. They break down, as its name might suggest, proteins, break peptide bonds. This one in your stomach and this one in your small intestine. That also should explain to you why this one we can see works best at a very low, which again means acidic pH. You know your stomach has stomach acid in it. Its pH is quite low. It's right around 2. This enzyme has evolved in a pH of 2 to work best. Why is that? Why does pH have an effect? Well, now again, I'm giving you some little extra, no extra charge, but in chemistry next year, you'll get a lot of this. What's pH all about again? It's about these two ions, hydroniums and hydroxides, and how many of these are compared to those. Remember, if there's a lot of these, that's what an acid's all about. Low pH number. If there's a lot of these, that's what a base is all about. But because these are charged, they tug and pull on other things that are charged. And all enzymes have some charged areas, as we've said. So now, hopefully you can start to understand. At a pH of 2, with a lot of hydroniums tugging and pulling on it, this molecule gets pulled into its working shape. At a pH of 2, this molecule would be pulled out of its working shape. And vice versa. At a pH around 8, a more what we would call normal pH, this one gets pulled and tugged out of its working shape, and this one gets pulled and tugged into. So now, we go analyze these graphs, and we describe and we explain. The description is this. A good description always includes numbers if it can. And there's no numbers on this y-axis, so I'm going to put some. I'm going to put 10, 20, like reactions per second, whatever. Okay? So here's a great description of this black line of the action of pepsin. From a pH of 0 to 2, the rate of reaction increases from 0 to 25. I have described the general idea. That's a qualitative description, increase, but I've also described it quantitatively, I said how much it increases from 0 to 25, and in quantitative terms, when the independent variable pH goes from this pH to that, 0 to 2. Now, to complete my description, I also can't forget about this part, right? From 2 to about 3.5 pH, the reaction rate goes from 25 to 0. Now, what's the explanation? Well, the explanation for this increase is not about more collisions, because nothing about pH is going to increase collisions like was true for both substrate concentration and temperature. The increased collisions was the reason for the increase in both of those, which look similar on the graph. The reason for this one is an increasingly well-fitting active site as pH increases, and then a decreasingly well-fitting active site as pH goes beyond this optimal pH. Make sense? Hope so. So now, real fast, because we're going to get back to these later a little bit, but enzymes, it turns out, we've learned that most of them can't work just by themselves, like our simple models showed. They need some help. Sometimes that's as simple as kinds of things we call ions, minerals in your diet. You know you need minerals. Well, here's a good reason why you need them. And sometimes these helpers, called coenzymes, are big organic molecules, some of which are vitamins, or at least parts of vitamins. We'll come back to them later, especially a couple of key specific ones that have to do with stuff in a different unit. Practice time a little bit, okay? So overheating an enzyme, oh, we just talked about that. I know about that, right? If we heat up the system, the enzyme works better until it hits that point where, boom, it doesn't work anymore. That was the graph part, right? It results in the enzyme's loss of what? Well, it had its shape change. Nothing about shape change here. Electrical charge, I haven't talked about anything that would change its electrical charge. Storing chemical energy, that is not what enzymes do. Don't ever say that, please. Store inherited information, that's the job of DNA and RNA. That's no good. Its ability to catalyze a reaction, though, is going to be decreased if that enzyme gets overheated, and that term implies that it was too much heat. That's what happens. What's the function of enzymes in biological systems? Enzymes act as substrates. You can pretty much stop reading there because these vocab words have specific meanings, and enzymes are not substrates. There's a reason for those two different words. They also don't act as products. They act as catalysts is what they act as. Here we go. Act as catalysts to drive chemical reactions forward. That's not a bad description, and chemists actually describe a reaction like this, A being split into B plus C, as being driven forward, like the direction of that arrow. But a multiple choice question, again, is asking for the best answer. So don't just get to a decent one and not read the other ones. Enzymes bond with substrates. Oh, wait a minute, that's pretty good. To create the new reaction products. That's kind of right, but remember what actually created the products was a collision. So if you read this literally word for word, you see the weakness of this answer. Enzymes combine with substrates, but they don't covalently bond to them to form products, and that's what this says. So while this is kind of okay, that's the problem with this description, and that's why this is the best answer.